Hello everybody. I am going to make a video for you today since I am out. I'd like for everybody to follow along, and hopefully you watched the videos that were posted in Canvas over the last few days since our last test. If not, you might be a little confused because I'm going to move kind of fast, but we're going to start out looking at page 2 on your notes, okay? So we're going to do a quick refresher on polynomials, but you do need to go back and watch the video on monomials and operations on polynomials if you have not yet, because otherwise, like I said, you might be a little confused about what's going on. Okay, so the first thing we're going to talk about is polynomials. What are polynomials? So polynomials is what we call the sum or the difference of many monomials. So anytime you have more than one monomial joined together with another monomial using addition and subtraction, you're going to get what's called a polynomial. All right, so like numbers 10 through 12, these are examples of polynomials right here. All right, so we've got more than one term, and you can see that they're joined together with plus signs and minus signs, okay? So number 10 is an example of 1, 2, 3, 4, 5 terms. So that's 5 terms. Number 11 is 1, 2, 3, 4 terms. And number 12 is 1, 2, 3, 4, 5 terms. So these are all polynomials. And we're going to talk in a second about the different ways that we classify polynomials. But for now, let's go ahead and talk about the fact that when we do have a polynomial, it needs to be in what is called standard form. And when it's in standard form, it will be written with your exponents in descending order. Well, what does descending order mean? Well, you're starting with your highest exponent and working your way down. So, for example, we also call the highest exponent the degree of the polynomial. So number 10, for example, the variable here is k. So we've got a negative k to the 5th minus 1 plus 8k minus 3k to the 3rd plus 1/4 k squared. So if we're going to put this in standard form, we're looking for the highest exponent on these k's. We can see that this is going to be our highest exponent, where it's a 5. So that's going to be the first term, negative k to the 5th. Now we're going to work our way down. So if we're starting with 5, the next one we're going to look for is a 4, and we see that there's not an exponent of a 4. So we're going to skip to the next one, which is a 3. So the next term in line is going to be negative 3k to the 3rd. All right, now we're looking for a squared, or to the 2nd power, and we've got one right there. So that's going to be plus 1/4 k squared. And then we're looking for a k to the 1st, which is going to be right there, and that's a plus 8k. And then we have a constant as our last term, which is a minus 1. So now this is in standard form because we started with our highest exponent of a 5, and we worked our way down until we had a k to the 0 term. K to the 0. Why is this k to the 0? Well, anytime we have anything raised to the 0 power, it's equal to 1. So k to the 0 is actually 1. So that's going to be 1 times 1, which is just 1. So we worked our way down. 5, 4, 3, 2, 1, 0. And that was what we call a constant term. Okay. All right, number 11, we're going to put it in standard form. So anytime you have more than one variable, you're going to use the alphabetical order as well. So A comes before B, so we're going to start with our A's, and then we're going to look for the term that has the highest exponent on the A. So that would be this 4a to the 3rd. So we're going to start with 4a to the 3rd. And we're going to work our way down. So we're looking for a squared now. Here's a term that's got a squared in it. Don't worry about the fact that it's got a b in it yet. We're not worried about that. We're focused on the a's. So a to the 3rd, a to the 2nd. Now we're going to be looking for an a to the 1st. So here's our a to the 1st term, and it's 7ab. And now we're done with the a's, so we'll move on to the b terms. We're looking for a b term that has not been used, that's got the highest exponent. It would be negative b squared. So there was 1, 2, 3, 4 terms. We have 1, 2, 3, 4 terms, and now we're in standard form. So you can try putting number 12 into standard form if you want to pause the video and try it. Okay, so since x comes before y, we're going to start with our highest x term, and that is going to be this term right here where we've got an x to the third power. So it's going to be 9x cubed y. Now we're looking for x squared term minus x squared. Then here's our x to the first, so it's positive 5xy squared. And now we can move on to our next variable, which is the y, minus y to the fourth, and our constant comes at the end. So these are all in standard form. Okay, now there's two ways that we classify polynomials, and it's by degree and by number of terms. So anytime we have a polynomial of 0 degree, that would be like x to the 0. Well, we know that that's going to equal 1, so we call this a constant. Okay, so really there's no variable in that term. It's just a number. All right, when we have x to the first, that's what we call a linear polynomial. X to the second is what we call a quadratic. That should be familiar because anytime we have an x squared, we've got a U-shaped graph called a parabola. That's a quadratic. The polynomial that's a third degree, or its highest exponent is a 3, is what we call cubic. Polynomial to the fourth degree is what we call quartic. So think about quarters. There's 4 quarters in a dollar. Sorry, not quarter, but quartic. And then x to the fifth is what we call quintic. Okay, like quintuplets, that's 5. Okay, then we also classify them by their number of terms. So it's kind of like in science class when you're classifying order and species, you do it by 2 ways, family or phylum and kingdom and species, that sort of thing. So we're going to classify it 2 ways. One by its degree, and then the other is going to be by the number of terms. So if it's just 1 term, it's what we call a monomial. If it's 2 terms, it's a binomial, like a bicycle has 2 wheels. And then if it's 3 terms, it's a trinomial. And anytime it's 4 or more, it doesn't have a special name. We just call it a polynomial of however many terms it is. So if it's 4 terms, it's a polynomial of 4 terms. If it's 5 terms, it's a polynomial of 5 terms, etc. Okay, so just for real quick, we're going to classify these. So number 13 is going to be a linear binomial. Number 14 is going to be a quintic trinomial, and it's in standard form. Number 15, there's only 1 term, and there's no variable, so this is a constant monomial. Number 16, our highest exponent is a 3, so this is a cubic, and then there's 1, 2, 3, 4 terms, so it's going to be a polynomial of 4 terms. Number 17 is a quadratic, and there's 1, 2, 3 terms, trinomial. Number 18, there's only 1 term, and it's a 4th degree polynomial, so it's quartic monomial. Okay, so that is a quick refresher on the polynomials and how we classify them. So now what I need for you guys to do is to go to page 20 in this packet. We're going to skip down to graphing polynomial functions. Okay? All right. Now, there's a whole lot going on right here in this formula. You're not going to have to know any of this, except what I want you to recognize is the fact that when we've got the first term, notice how it's a sub n x to the n. So that first exponent is an n. The next one is n minus 1. The next one is n minus 2. We work our way down until we're like x squared, and then x to the first and x to the 0. Okay, so basically what this is telling you, and you'll never have to write this thing, but I just want you to recognize that every term, our exponent is decreasing. So let's say that n is 5. Well, then n minus 1 would be 4, n minus 2 would be 3, so on and so forth, until we work our way down in descending order to a constant term at the end. So a polynomial function will be in standard form. Also, I want you to notice that all of the coefficients, meaning the numbers that come in front of the variables, are real numbers. So they're not going to be imaginary numbers. They're going to be real numbers, and they're not going to be fractions. They're going to be whole numbers. Okay? And it will never be 0. So it will be an integer. Okay? All right. It could be a negative number or it could be a positive number, but our exponents will always be positive or 0. All right, that's what I want you to remember about this. You're never, like I said, you're never going to have to write it. And then the degree of the polynomial function is the value of the greatest exponent. So whatever the biggest exponent is, let's say it's a 5, then this would be a 5th degree polynomial. If our largest was a 4, it would be a 4th degree polynomial, and that we know that's a quartic. Okay? All right, now let's go back and talk about parent functions again. Before any transformations have been made, the most basic functions that we're going to have are these right here. So a constant, meaning that there is no variable. Remember, f of x is a fancy way of writing y, so f of x would equal some number, and we're just going to put c for a constant. Okay, let's say, for example, f of x equals 3. Well, f of x is a fancy way of writing y, so that would be like y equals 3. Well, anytime we have y equals, it's actually a horizontal line. So there's the graph of that function, y equals 3, or f of x equals 3. Okay? All right, a linear function would look like this. The parent function is f of x equals x. If we don't see an exponent on that x, it's understood to be a 1. So it's f of x equals x to the first. All right, so what this looks like is it's a linear, so it's a line, all right? Not a horizontal line anymore. It's going to be a line that's got a slope of 1, because 1x, and it goes through the origin, plus 0. It's in slope-intercept form. So the most basic linear function is going to have a y-intercept of 0 and a slope of 1, up 1 over 1, up 1 over 1, up 1 over 1. And it's going to give us a line that looks like this. Okay, sorry, I'm kind of crooked. All right, so that is the parent function of the linear functions. All right, the parent function for a quadratic is f of x equals x squared. So this is going to be a parabola that has a vertex at 0, 0, and it opens up. So it makes a U-shaped graph. All right, the cubic function is f of x equals x to the third. So what this looks like, this side still looks like the parabola, but the difference now is this side goes down, opens down. So it's got one arm that opens up and one arm that opens down. So I want you to be sure that, write that again so you see that it's an x to the third. It's a 3. Okay, a quartic, f of x equals x to the fourth. This is before any transformations have been made to it. Looks very similar to a parabola. It's just a little skinnier. Okay. So after there's transformations made, it could look a lot different than that. But it's got the basic characteristics of a quadratic, where both of the ends are going in the same direction. They're either both going up or they're both going down. Okay, and then the same, the quintic parent function is f of x equals x to the fifth. All right, this looks very similar, has the same characteristics as a cubic, where one arm is opening up and one arm is opening down. It's just skinnier. Okay, a little skinnier than the cubic. All right, one thing I do want you to notice, that anytime your exponent or our degree is odd, like x to the first, x to the third, and x to the fifth, Our arms are going in different directions. One is opening up and one is opening down. Notice on the linear, one is opening down, one is opening up. On the cubic, one is opening down, one is opening up. And the quintic, same thing. When our degree is even, like 2 and 4, then the ends are doing the same thing. Either they're both opening up or they're both going to be opening down. And we're going to talk about that later, okay? So just keep that in mind as we move into this. All right, let's look at this example of a graph of a polynomial right here. Here we've got an end that's opening down and an end that's opening up. So if we're riding this thing like a roller coaster, we're coming in from the left to the right, like we always read a graph. We're headed uphill on our roller coaster. We hit the top, and there's actually a point up there where the graph changes direction, and now it's coming back down. It's coming down, coming down. It hits a point down here where it changes direction, and it turns, and it starts to come back up. So these are what we call the turning points of the graph, okay? So the points at which the polynomial function switches direction, it's called the turning points. If the turning point is higher than any other point nearby, we call it a relative maximum. And if our turning point is lower than any other nearby point, we call it a relative minimum. So it's a low point. Now it's not the lowest point on our graph, because if we look at this little arm over here, there's points that are lower than it, and it keeps going to negative infinity. And this is not the highest point on our graph, because there are points on this side, this little arm that keeps headed up towards positive infinity, that are higher than this point. But because it's the highest around and it's a turning point, it's a maximum. And this one's the lowest around, so it is a minimum. If we can find the absolute maximum point, let's say it stops up here or it stops down here and it doesn't go any higher, and we have found the absolute maximums or minimums, we call those extrema. But we don't have any of those on this graph because this goes up forever and ever to infinity and beyond, okay? So let me clean this up a little bit and let's go and look at it again. All right, so we've got our turning point right here. We've got our turning point right here. So it's where our graph changes from an increasing to decreasing, from decreasing to increasing. So when we're talking about increasing and decreasing, we're going to be talking about the intervals on the x-axis over which that occurs. So if we're coming in from negative infinity, okay, here's negative infinity, all the way down here on the left is negative infinity. So our graph is increasing, meaning it's going up, 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 and then it's stopping right here. So from negative infinity to this point right here on the x-axis, we have a positive or an increasing interval. From this point to this point, so in between, is where our graph is decreasing. So that's a decreasing interval from whatever this x-coordinate is to whatever this x-coordinate is right there. And then it turns again, and now it's increasing. And it's increasing from whatever this x-coordinate is to positive infinity. So we're going to talk about our increasing and decreasing intervals next. Before we do that, let's move on to, page 21. This thing flips that way. Okay. If you haven't got one yet, go ahead and pause this video and go get yourself a graphing calculator. Okay, so everybody should have a graphing calculator now. And what I want you guys to do is I want you to go and find the button that says y equals, okay? So go find the y equals button. It's in the top left corner, y equals. When you hit y equals, it brings up places for you to enter your equation. So if there's anything written, go ahead and hit clear. Clear that out. We're going to practice typing in this equation. So this is the polynomial that we're going to type in. Y equals x to the third minus 6x squared plus 7x plus 2. Okay, you might be wondering, how do I type in x to the third? All right, on your keyboard there, on your calculator keyboard, you're going to look for the button that's got like an X and a T and a theta all on it together. It's over kind of on the left side next to the second button, okay? So when you see that, this is how you're going to access your X's, okay? Whenever you need to type an X, you're going to push that button. If you need to raise it to a power like x to the third, on the right side of your calculator, over there by the plus and minus sign, you're going to see a sign that looks like this. Looks almost like a little upside down V. Call it a caret, okay? So anytime you need to raise an x to a power, you're going to hit X using this button right here. You're going to go over and you're going to hit this caret, and then you're going to raise it to whatever number. So x to the third. So go ahead and try that. Now your cursor is still up there next to the 3. You're going to use your arrow keys, arrow to the right to get out of the exponent, and it'll put your cursor back down level with the x, and you can finish typing in your equation. So you're going to type x to the third minus 6x squared. You can use the caret again and raise it to the second power, or there is actually a button that's got x squared, and it will put an exponent of 2 on your variable. Then plus 7x plus 2. All right, so practice that. Pause this video if you need to practice that. But when you plug that in your calculator, and if you feel like you've entered it correctly, you want to try to graph it. So you're going to go over to the top, and you're going to hit the button that says graph, and it should graph this thing for you. Okay. All right, so the graph of this polynomial is going to look something like this. Okay, something like this. So we see that it's the left end is pointing down, the right end is pointing up, and we're going to have some relative maximums and relative minimums. So we're going to figure out what those values are. So what you're going to do is you're going to hit the trace button. This seems kind of like some extra steps to me. We're not going to worry about doing this. But you're going to go up to the top, and you're going to find the button that says trace. And when you hit that button, it's going to put a little X on your graph. That's your cursor. So you can move that cursor around, and it can go up and down your graph by using the arrows, the right and the left arrows on your, we've got the little round part on your keyboard. We're not going up and down. We're going side to side from left to right on our graph. That's why you're going to use the arrows that go from left to right. So you can trace and move along your graph by using the right arrow, or you can move back by using the left arrow. But you're going to try to position your cursor at the very, very top, and it will tell you the x coordinates and the y coordinates at the bottom for all of your points. So once you have traced this one, you should see that the relative maximum of this point is somewhere, sorry, just a second. Let me get my little cheat sheet here. Oopsie. On page 20. Somehow my notes got out of order. Solving by graphing. Where are you? Hold, please. So you can keep practicing typing these things in. I apologize for the delay, but I don't want to start this thing over. Okay. Here's my notes. Okay, I can't find the page that's got, oh, I know why. I let a student borrow it yesterday and I didn't get it back. So you're going to find that your relative maximum, patience, grasshopper, x to the third, let me type it in my calculator because I can't find my notes, times x squared minus x squared plus 7x plus 2. All right, sorry about that. So our relative maximum is going to be like 0.71. Anything close, okay? It's not quite accurate. It's hard to tell with that, but there's such small decimal numbers, I'm not too worried about it. So we're just going to round to the nearest hundredths place. And then the y-coordinate of that relative maximum should be somewhere around 4.30, okay? So that is the relative maximum, meaning it is that the top, as we're coming in from the left, increasing, we hit this turning point, we start to turn and go down. So this is the relative maximum. So that's going to be 0.71, 4.3. All right, you can keep arrowing over with your cursor and go to that relative minimum down there, and it's somewhere close to 3.3. And then the y-coordinate is negative 4.3 as well, okay? So anything close to that would work. All right, then we want to talk about our increasing intervals. So let me clean this up just a little bit. If we know that we've got 4.3, a graph that looks something like this, and this is 0.71, 4.3, then we're increasing. We're coming in from negative infinity, and it's increasing until we hit this point. Well, the x-coordinate of that point is 0.71. So our increasing interval is going to be from negative infinity to 0.71. So it hits this turning point, and now it starts to decrease. It decreases until it gets down here to this relative minimum. And we know that the x-coordinate of that point was 3.3, okay? And then the y, which I erased, was negative 4.3. So it decreases on the over the x-axis from 0.71 to 3.3. Then it turns and it starts to increase again at 3.3. And it keeps increasing until positive infinity. Okay, so this is how we determine our increasing intervals and our decreasing intervals. So we'll practice one more right now. Okay, all right, so go ahead and go back to y equals on your calculator. Go ahead and clear that line. Now you're going to enter y equals x to the third minus 3x squared minus 3. Okay, once again, we get something that resembles that, that last one where one end is pointing down and one end is pointing up. But go ahead and graph it and hit your trace button. And this time, these points are a little prettier. Our relative maximum is going to be 0, negative 3. And our relative minimum is going to be 2, negative 7. Okay, so those look a lot better without those decimals. So let's go ahead and plot those points on this graph over here. 0, negative 3 is going to give us a point right here. No, it's not. I went too far down. Sorry. 0, 1, 2, 3. It's going to be right here. And then our relative minimum is 2, 7. So we're going to go over to 2 and down to negative 7. And there's that relative minimum. So our graph is coming in from the left. It hits that turning point. It turns, goes down, hits that turning point, and now it's increasing and it's heading up to positive infinity. So guys, this is ugly. It doesn't have to be perfect. It's just a sketch, okay? but this gives us an idea of what our graph is going to look like. Now, first of all, let's identify something. Our leading term right here, x to the third, we can see that our exponent is an odd number. So it's an odd degree, okay? If it's an odd degree, like we said earlier, our arms are going to be doing different things. One is going to be going up and one is going to be going down. Okay, so that's how we know that it's going to have some turning points somewhere. All right, this one has 2 turning points, and we had a degree of 3. So we're going to have one less turning point than we have degrees. So if it's a 3rd degree polynomial, we're going to have 2 turning points. If it's a 4th degree polynomial, we'll have 3 turning points. If it's a 5th degree polynomial, we'll have 4 turning points, so on and so forth, okay? So we just need to recognize that when we see that odd degree, we know that we have ends going in different directions. Okay, the domain, it keeps opening to the left and it keeps opening to the right, so our domain is all reals, all real numbers. And the range, there is, even though there's a relative minimum and a relative maximum, it still keeps going up forever and down forever. So the range is also all reals. So don't forget, domain is all the x values and the range is all the y values. Okay, now let's talk about the increasing intervals. When we're talking about the increasing intervals, we're talking about the x-axis. What portion or what segment, what interval of the x-axis do we have increasing? So we're coming in from negative infinity and it's stopping right here. This is where it stops to increase and it turns and becomes decreasing. So from negative infinity to this point on the x-axis, we have an increasing interval. So that's from negative infinity to where x is 0. Now from 0 to this point right here, it decreases. Now what is that on the x-axis? Well, it's where x is 2. So between 0 and 2, our graph is decreasing. Then it makes another turning point, or it hits another turning point, and now it starts to increase again. So that starts at 2 and heads out to positive infinity. So that is our increasing interval, our second increasing interval. So 2 turning points gives us 3 intervals. In this case, 2 of them were increasing intervals and 1 was decreasing. And then going back to our quadratic unit, we talked about end behavior. So you're really just looking at the ends of your graphs and seeing if they're pointing up or pointing down. This one says as x approaches negative infinity. So that means the left side. Okay, so x is approaching negative infinity on the left end of your graph, and x is approaching positive infinity on the right side of your graph. So there's as x approaches negative infinity, it's saying, look at the right side of your graph, and what is the arrow doing? It's pointing down, so that means our y's are headed to negative infinity. And this says, look at the right side of your graph, what is your arrow doing? It's pointing up, so that is headed to positive infinity. Okay, so that's what's happening with those. All right, we're going to do number 2 a little bit faster. So we've got x to the 4th plus x to the 3rd minus 4x squared plus 5. So everybody go to your y equals button and clear it out. You're going to type that in, x to the 4th plus x to the 3rd minus 4x squared plus 5. Okay. All right, first thing I want you to notice is when you hit graph and you see the graph of this thing pop up, that the ends of your graph are going the same direction. They're both pointing up, aren't they? The ends. Well, that tells us our end behavior right there. They're both headed to positive infinity. Notice that our exponent was even. So if our exponents are even, our ends are going to be doing the same thing, and they're both pointing up. Okay? Now we're going to find out in a minute how to tell if they both point up or if they both point down. But if they're even degrees, if our leading term is an even degree term, then our ends are going to be going the same direction. Okay, so let's go ahead and hit the trace button. And now we can find our relative maximums and our relative mins. So if we start on the left, we have a low point. Our first turning point is a minimum. It's down there at the bottom. So look, we're going to round to the nearest tenth here. We should almost just round to whole numbers, but we're going to just use decimals. So this is a relative minimum because it's a low point. So the x-coordinate should be something like negative 1.8. And then the y-coordinate is negative 3.3. Something like that. Anything close, okay? Those are some small decimal numbers. So then it turns and we head up, 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 up. We go to the very top and we see we get to a point, and that's a relative maximum, 0, 5. Then we use our cursor and we keep tracing, tracing, tracing to the right. And we're going down, 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 and we get to another relative minimum. And the coordinates for that relative minimum are like 1.0888. So we're going to round to 1.09. And then the y-coordinate for that point is 2.95. So that's going to round this up to 3, basically. Okay, so we have 2 relative minimums and 1 relative maximum. So now let's talk about the domain. Notice that our ends are both pointing up forever and ever in this thing. You could just keep tracing forever and it goes up forever and ever and ever. So as it goes up, it's going to get wider and wider. So our domain is all reals. Now this time we have to be careful with our range, because if both ends are pointing up, it's not heading down forever. We do have a low point right there. That relative minimum that we listed first is actually the lowest point on this graph. So it is actually the extrema. So it's the lowest point. And it is at, the y-coordinate for that point is negative 3.3. So when we're talking about our range, we're going to look at that y-coordinate of our lowest point, and the y values are going to be everything greater than or equal to that y value. Y is greater than or equal to negative 3.3. Okay, so let's go ahead and plot this. Let's use this relative minimum, and we're just going to kind of go over to negative 2 and down to negative 3. It's just a sketch, so it doesn't have to be perfect. It's a little lower than negative 3. Then we have a relative maximum at 0, 5, so go to 0. And we're not moving to the right or the left, but we're going up 5. 1, 2, 3, 4, 5. And then our other relative minimum is at 1.09, which is almost 1. And then up 3. 1, 2, 3. So we're coming down from negative infinity, hitting that turning point, going up, hitting that turning point, going down, going back up. So our graph is going to look something like this. Okay, it's a sketch, so it doesn't have to be perfect. Alrighty, but there is the graph, and now we just need to determine our increasing and decreasing intervals. So if we're coming in from left to right like we read a book, we're actually going down. So we're decreasing from negative infinity to this point right here. Okay, so this is negative infinity, so we're decreasing over the x-axis, decreasing until we get to this point. Well, we've already said that the x-coordinate of this point is negative 1.8. So our first decreasing interval is from negative infinity to negative 1.8. Now, our increasing interval starts right there at negative 1.8, and it increases until we get up here to this point. And the x-coordinate of that point is 0. Okay. Then it decreases again from 0 to this point right here, and the x-coordinate of that point is 1.09. And then it starts to increase again at 1.09 and heads to positive infinity. So if you need to rewind that and see how we did that, feel free. But whenever we're talking about increasing and decreasing intervals, we're talking about the x-axis. Where along the x-axis is our graph decreasing, and where is it increasing? Okay, now there's one more thing that I want to talk about, and that is on page 23 of your notes, okay? So remember, we already talked about the lead term and how the lead term affects the ends of our graph. So looking at number 1, what I want you to see about number 1 is the lead coefficient. We're going to call it LC for short. The LC, the lead coefficient, is a positive 3. And we have a degree of 2. Well, 2 is an even number, okay? So we know, because it's got an even degree, that our ends are going to do the same thing. They're either both going to point up or they're both going to be headed down, okay? But what we look, now we got to figure out, well, are they opening up or are they opening down? Well, this lead coefficient, this number in front, tells us if they're opening, if it's opening up on the right side or if it's headed down on the right side. If it's positive, it's headed up, okay? So what that means is the right end of this graph is headed up. Now, because it is an even power, that x squared tells us that both sides are doing the same thing. Okay? So if it's an even degree, your ends are doing the same thing, and the lead coefficient tells you if it's opening up or opening down. So it tells us what the right side is doing, opening up, and since it's an even, the other side is doing the same thing. So our end behavior for number 1 is that both ends are headed up, so towards positive infinity. All right, we're going to try another one. Number 2, our lead term. The lead coefficient is actually a -1. So if our lead coefficient is a -1, that tells us that our right side is opening down. Okay? So now we're going to look at our degree. If our degree is a 2, it's even. So that means that our sides are doing the same thing. So that means both sides are headed down. So negative infinity and negative infinity. As x approaches negative infinity, so the left side is headed down. As x approaches positive infinity, the right side is headed down. Okay, look at number 3. Lead term. Our leading coefficient is a positive 2. So that means our right side is going to open up. Now look at our degree. The degree is a 3. It's odd. So if it's an odd degree, what I want you to think is that the ends are at odds with each other. So if it's an odd degree, 1, 3, 5, 7, the odds, then your ends are at odds with each other. So if the right side is pointing up, and we know it is because our lead coefficient is positive, then that means the left side will be pointing down. They're at odds with each other, doing opposite things, okay? Another way you could remember it is when you think something is odd, it's different, right? So if you think somebody is odd, you think they might be a little different, then same thing with this. If we have an odd degree, our ends are different. So the right side is, we're told the right side is going up because our lead coefficient is positive. So the lead coefficient tells us what the right side is doing, and the left side would do the opposite. So now we just got to figure out which is the left and which is the right. So as x approaches negative infinity, that's the left side. So that's negative infinity. And as x approaches positive infinity, that's the right side, so it approaches positive infinity. And it's kind of messy. I'll try to be a little neater on this next one. On number 4, our lead coefficient is a -1. The number in front of the x cubed is a -1. So what that tells us is the right side of our graph is headed down. Negative means it's headed down. Okay, so now what we look at is our degree. The degree of the polynomial is odd. So if it's odd, our ends are at odds. So if the right side is headed down, the left side is headed up. So now we just have to determine which is the left side and which is the right side. So as x approaches negative infinity is going to be the left side. So our left side is headed to up, so that's headed to positive infinity. As x approaches positive infinity, it's the right side of our graph. So we already know the right side is headed down to negative infinity. All right, let's try number 5. Our lead coefficient is a +1. And it's a degree of 4, so it's even. So if it's a lead coefficient of a positive, our right side is headed up. And an even degree means they're doing the same thing. So they're both headed to positive infinity, both ends of the graph, the end behavior. Number 6, our lead coefficient is -1. So if the lead coefficient is negative, that means the right side is headed down. But our exponent is even, so that means both sides are doing the same thing. So as x approaches negative infinity, as x approaches negative infinity, y is headed to negative infinity, it's headed down. And as x approaches positive infinity, y is headed to negative infinity. They're both headed down. Okay? So here's a little chart that might help you. If our leading coefficient is positive, that means the number in front of the x is positive. Then that means our right end opens up. Okay? And we know that if the degree is even, then the other side is opening up too. If our leading coefficient is negative, that means the right side is opening down. And if the degree is even, that means they're doing the same thing. So these are the end arrows of our graph. All right, now let's go back to a positive leading coefficient means our right side will be headed up. But since our degrees are at odds, it's odd like 1, 3, 5, then our left end would head down. If our leading coefficient is negative, then that means our end is heading down on the right. But since they are at odds, the left side is headed up. So hopefully this little chart can help you as we move into the next section. I'm just going to try 1 or 2 with you, and then your job for the rest of the day is to finish page 23 and page 24 and fill in the end behavior for these things. So number 7, we have f of x equals -5x plus 1. I want you to take a look at the lead term. Our lead coefficient is -5, and our degree is odd. Okay, so we know that if our leading coefficient is -5, so we'll fill that in here, sorry. Our leading coefficient is negative, and our degree is odd. That's where that's going to go, okay? So we know our end behavior on the right side is going to be headed down because our leading coefficient is negative. And our ends are at odds, so the left end would be headed up if the right end is headed down. All right, number 8, our lead term. Our degree is even. It's a 2. And our leading coefficient is 12, which is a positive number. So if it's positive, it means the right side is pointing up. Well, we just have to look at our degree now. If it's even, both sides are doing the same thing, so both ends are headed up. Okay, I want you to do this again and finish 9 through 14 the same way. Then number 15 and 16, you're just going to look at your ends and determine if you have a leading coefficient that is positive or negative, and if your function has an even or an odd degree. So for number 15, we can tell that since both ends are headed down, that we have a negative leading coefficient, negative LC. And then since they're both headed down, our ends are doing the same thing, we have a degree that is even. Okay, so try number 16. And then on 17 through 20, you're going to look at your end behavior and see which of these following functions will fit the category. So what we know is if we've got end behavior where they're both negative, then our LC is negative and our degree is even because they're doing the same thing. So that is going to limit it to this one and the last one, because our leading coefficient has to be negative. Well, here's a negative, but it's got an odd degree. That won't work. Here's a negative, but it's got an odd degree, so that one won't work. So the only ones that will work are going to be this one and this one. So that's what we're doing. Figure out what your LC is and if your degree is even or odd, and then determine which functions will satisfy that end behavior. Okay, guys, that is it for today. That was nice and long, but I hope that you were able to follow along. You can pause it, rewind it, and go back and check out anything that you might not have understood the first time. And I will see you on Thursday.